Friends, very good morning to everyone. We were looking at the reactions of the carbocations. We know that it can undergo addition reaction, substitution reaction, elimination reaction, and also a rearrangement. We have seen a rearrangement where 1, 2 hydrate shift has taken place, and 1, 2 alkyl shift and 1, 2 aryl shift. One of the examples of the rearrangement reactions which a carbocation can undergo is pinacol-pinacolone rearrangement. This is today's subject of discussion. This rearrangement was first described by Wilhelm Rudolf Fittig in the year 1860. This is the conversion of vicinal diols, that is 1, 2 dihydroxy compound to carbonyl compounds on treatment with acids. Example for this is 2, 3 dimethyl butane 2,3-diol, that is pinacol, reacts with acid to give rise to tertiary butyl methyl ketone, that is pinacolone. If I look into the reaction mechanism, this is 1, 2 diol, 2, 3 dimethyl butane 2,3-diol. We have the methyl groups at 2 and 3 position and OH group at 2 and 3 position. This is pinacol. Pinacol, when it is treated with an acid being a proton donor, OH has lone pair of electrons and that gets protonated and it gives rise to OH2 plus. It has to maintain its divalency. That's why to satisfy this positive center, the carbon and oxygen bond breaks. And these electrons are taken away by this oxygen, giving rise to a carbon with a positive center, that is carbocation. As carbocation is formed over here, it has to be stable. That's why the adjacent carbon and its substituent, the bond breaks. This substituent on the adjacent carbon along with its electron pair moves towards this positive center which is formed, and once this electrons are taken away from the adjacent carbon, a new carbocation is formed. Here 1, 2 alkyl shift has occurred. That is, the alkyl group from the 1 position has shifted to the 2 position. That's why this is a rearrangement. Then, to satisfy the newly formed positive center, the bond between the oxygen and hydrogen breaks and these are taken away by this carbon and it loses H plus. H plus is a catalyst. Hence, I'll get a rearranged ketone. This reaction is called as pinacol-pinacolone rearrangement. Here, which group should migrate? If a group, an alkyl group, which is having more electron richness, will migrate more easily. If there is a tertiary alkyl group has more migratory aptitude than cyclohexyl, has more migratory aptitude than secondary alkyl, than that of benzyl, and so on and so forth. In case of aryls, if it has a electron donating group on the aryl group, that group shifts preferably. For example, para-methoxyphenyl group shifts more easily than para-methylphenyl, than that of para-chloro, than that of para-bromo, than that of para-nitrophenyl groups. But however, which group should shift is pre-decided by which group is protonated. Which OH group is protonated? If I take a vicinal diol like this, in which one carbon is attached with anisile, another carbon is attached with paranitrophenyl group. Here, there are two OH groups which are equally having opportunity to get protonated. Here, the OH group to which the anisile group is attached gets protonated rather than the OH group to which the paranitrophenyl group has got attached. Why is it so? Here, if the protonation of this OH occurs, these electrons, it gives H2O, and these electrons moves to this positive center and it loses as water molecule. It gives rise to a positive center on this carbon. This carbocation which is formed is more stable because of this methoxy group which is present on the aryl group. It is an electron donating group, that's why it becomes more stable. If at all this group has got protonated, positive center group might have arisen here, but however, this won't be very stable because here the adjacent group phenyl has an electron withdrawing group. That's why the carbocation found won't be stable. Hence, the which group should migrate depends upon which OH group gets protonated. Now, paranitrophenyl and phenyl. Phenyl group has more electron density. That's why migration of the phenyl group towards this carbocation occurs. And deprotonation of this OH occurs to give rise to a rearranged ketone. If I take cis 1,2-dimethyl cyclohexane 1,2-diol and treat with an acid, the protonation of this OH group occurs. It loses water molecules and the positive center which is arised, a carbocation, and the adjacent carbon, the methyl group which is there attached to it will shift towards this positive center to give rise to corresponding ketone. The OH group, that is the living group, and the migrating group, they should be opposite to each other for the reaction to occur. The one which is opposite to the living group will shift. This is another requirement for pinacol-pinacalone rearrangement. For example, if I take trans 1,2-dimethyl cyclohexane 1,2-diol, it gets converted into a 1-acetyl 1-methyl cyclopentane. Here the ring contraction occurs. How is it? Let us look at. You will get 1-acetyl 1-methyl cyclopentane. If I look into the mechanism, the protonation of the OH takes place leading to OH2 plus. This OH2 plus will take away the electrons and go away, creating a carbocation. Now, the OH bond breaks, the electrons form the double bond over here, and here the opposite to the living group, this is also a beta carbon, this is also a carbon. This won't shift over here, but here this bond break over here and this shifts over here. That's why ring contraction occurs to give 1-acetyl 1-methyl cyclopentane. This is the stereochemistry here. The living group and the migrating should be opposite to each other. That's why trans 1,2-dimethyl cyclohexane diol gives a different product from cis 1,2-dimethyl cyclohexane diol. We can also see ring expansion reactions in utilizing this pinacol-pinacolone rearrangement. If I take cyclopentyl diol, if I treat with an acid like H2SO4, protonation of the OH takes place and this OH2 plus leave away as water molecule, giving rise to a positive center on this carbon from which the water group has left. The OH bond forms a double bond and the carbon from here shift towards this positive center. 1 comma 2 alkyl shift occurs and now the ring expansion has occurred to give corresponding expanded ring system. This is another application of this pinacol-pinacolone rearrangement. This rearrangement was modified slightly by Tiffanow-Demjanov, and that's why it is named after them as Tiffanow-Demjanov reaction. Here, instead of diols, vicinal diols, we have taken 1 comma 2 amino alcohols or amino carbenols. Here, vicinal amino alcohols are taken. When it is treated with nitrous acid, it gets converted into rearranged ketone. This is also used for synthesizing ring expanded cyclic ketones. The Demjanov reaction says like this. This is an vicinal amino alcohol. In case of pinacol rearrangement, there are vicinal diols. 1 comma 2 diols were there. Here it is vicinal amino alcohol. The amino group, when it is treated with nitrous acid, it forms a diazonium group. To satisfy the positive center on this diazonium group, the electrons moves, creating the positive center over here, and the 1 comma 2 alkyl shift from the adjacent carbon takes place and creating a new positive center, that is the carbocation on this adjacent carbon from which the alkyl group has moved, and to satisfy this positive center, the electrons from the OH moves towards to give rise to a rearranged ketone. This is an extension of pinacol-pinacolone rearrangement. If I take amino alcohol with cyclohexane ring, when it is treated with nitrous acid, I'll get corresponding cyclopentyl carbaldehyde. If I take 1 aminomethyl cyclohexanol and treat with nitrous acid, it gets converted into corresponding cycloheptanone. This is the application of this Tiffanow-Demjanov reaction. Another rearrangement which a carbocation can undergo is neopentyl rearrangement. This is also called as Wagner-Mirvin rearrangement. Wagner reported this rearrangement for the first time in the year 1899, and further it was extended by Mirvin in the year 1914. Hence, they are named after them. Here, I take tertiary butyl bromide and make it to undergo hydrolysis under SN1 condition. I'll get 2-methyl 2-butanol instead of tertiary butanol. This is because of this Wagner-Merwin rearrangement. If we look into the mechanism, I take tertiary butyl bromide. It reacts with H plus, Br minus moves away and combines with H plus and loses as HBr, creating a tertiary butyl carbocation. This is a primary carbocation. The primary carbocation is unstable. To satisfy this primary carbocation instability, the alkyl group present on the adjacent carbon takes away its electrons and along with its electron pair moves towards this carbon. Once it moves, we get a new carbocation from where the alkyl group has got shifted. Here 1, 2 alkyl shift has occurred to give a new carbocation. This carbocation is attached to 3 carbons and it's a tertiary carbocation. And we know that tertiary carbocation is more stable than the primary carbocation, and hence this is the driving force for the this 1, 2 alkyl shift. And on this new carbocation which is formed, OH minus attacks and I will get corresponding to hydroxy 2-methyl butane. If at all I won't supply this OH minus, the carbon hydrogen bond on the adjacent carbon breaks and those electrons are utilized to satisfy this positive center and it gives rise to 2-methyl 2-butane. This formation of 2-methyl 2-butane is an indication that the 1, 2 alkyl shift has occurred. This is Wagner-Merwin rearrangement. This has been utilized for the synthesis of few natural compounds. Alpha pinene, if I take and treat with HCl at minus 10 degrees centigrade, I'll get 1, 2 addition and I'll get corresponding H and Cl added onto the double bond. I'll get an halide. This can undergo Merwin rearrangement. This can dissociate, loses chloride ion and it gives rise to a positive tertiary carbocation over here. Here in this system, there is a 4-membered ring system in here. This is less stable. Then this less stable ring system undergo Wagner-Merwin rearrangement at minus 20 degrees centigrade. What is it? 1, 2 alkyl shift. At this one position, there is a positive center and here 2 position alkyl group. From here, the bond breakage occurs and this shift towards this positive center. And I'll get a 5-membered ring with a positive center. This shift occurs because 5-membered ring has more stability over the 4-membered ring system. And this can react with Cl to give rise to corresponding bornyl chloride. The bornyl chloride can be converted to camphene by Wagner-Merwin rearrangement. This 5-membered ring system can undergo Wagner-Merwin rearrangement at minus 20 degrees centigrade. The alkyl group here shift towards this, giving rise to another tertiary carbocation. To satisfy this positive center, the carbon hydrogen bond breaks and electrons are utilized to form the double bond and gives rise to caffeine. This is the utility of this Wagner-Virwin rearrangement. Next class, we can deal with the new topic in the same carbocations. Till then, have a nice day. Thank you.